So last time we talked about oxidation reactions, and this time we'll learn about reduction reactions, several different ones. These reactions need suitable reducing agents, such as, there's a couple of them here that you need to know, sodium borohydride, or NaBH4, in either aqueous or alcoholic solution. So that could be a solvent of ethanol is our alcohol, or just an aqueous solution. Another option, and again, it's either one of these. There's one that's more suitable than the other for particular reactions. I don't think we're going to get into that much detail. So the next one is lithium aluminum hydride, LiAlH4, in anhydrous conditions such as dry ether, like a diethyl ether, followed by an aqueous acid. So depending on the reaction conditions, one may be more suitable than the other. What they both have in common is that they produce the hydride ion, H minus, which acts as a reducing agent. Now I had a little issue with the font here, so it's plus H, and we saw in the last lesson plus O for oxidizing agent, plus H is for our reducing agent. Or I've also seen it as the plus H in parentheses, so it's not, shouldn't be like way up here. So either one of those for our reducing agent. Let's take a look at some examples. I'll start off with the reduction of a carboxylic acid. So remember, how did we form a carboxylic acid? Well, we can take an alcohol and oxidize it under reflux and get the carboxylic acid. So remember, primary alcohol can first oxidize to an aldehyde, which then can further oxidize to a carboxylic acid. So for this particular reaction, we're going to use lithium aluminum borohydride. No, wrong one. Sorry, lithium aluminum hydride. And unfortunately, we can't stop this reaction at an aldehyde if this reaction occurs in diethyl ether. So let's just take a look at a generic equation. Could be any carboxylic acid, ethanoic acid. So again, we want to show that it is being reduced. It is first reduced to an aldehyde. And then the reaction again happens too fast to stop it at an aldehyde. So it then is reduced, the aldehyde is reduced to a primary alcohol. So again, opposite of what we saw in the last lesson where we were oxidizing a primary alcohol to an aldehyde or carboxylic acid. This time we're reducing a carboxylic acid to an aldehyde and then to an alcohol. All right, for ketones, the reduction of a ketone happens best using sodium borohydride in an aqueous solution. And this is going to produce, of course, a secondary alcohol. So just a complete opposite of what we saw in the last lesson. And then lastly, we can reduce an aldehyde. This reaction will occur via lithium aluminum hydride. And this reaction will produce a primary alcohol. So again, very much the opposite of what we saw with oxidation. Make sure you're familiar with reducing agents, either lithium aluminum hydride or sodium borohydride. So either one is going to produce the hydride ion, which acts as our reducing agent. All right, here's another one you need to know. It involves the nitrobenzene, reduction of nitrobenzene. This process, the reduction of nitrobenzene, is going to result in the formation of aminobenzene or aniline. So this time we need our conditions, reaction conditions. We need tin and concentrated hydrochloric acid, and this will be heated under reflux. So let's take a look at this equation. So our first step, tin and concentrated hydrochloric acid. This is going to produce this ion. This is known as phenylammonium. As you can see why we have NH3 plus is kind of our ammonium, and then a benzene ring we can name as phenyl. So phenylammonium. Next step involves the addition of sodium hydroxide. The sodium is just a spectator ion, so all we care about is the hydroxide here. So let's take a look at that. And so the addition of hydroxide is going to remove one of the hydrogens from the phenylammonium ion. And so we're going to end up with our organic product, which is aniline or aminobenzene, and we get water. So again, we have tin, which is our source of electrons, and concentrated hydrochloric acid heated under reflux to form first the phenylammonium ion, and then further a reaction with hydroxide to produce our desired results. All right, changing gears a bit, we'll just go in the order of your notes. We talked a little bit about physical properties, and physical properties are being a result of the strength of the attractive forces between particles. So let's look at the difference in physical properties of some of these organic compounds that we've been working with. First of all, carbon chains are nonpolar unless there's different functional groups that are attached to the carbon chain, such as hydroxyl groups or amino groups. But as a whole, just a hydrocarbon chain is nonpolar. In fact, you can have a really large molecule that has a long carbon chain that maybe has a hydroxyl group on the end, and it'll exhibit kind of properties of both a nonpolar and polar molecule. So that carbon chain, there'll be dispersion forces between carbon chains of different molecules, and then of course you'd have hydrogen bonding between hydroxyl groups of different molecules. So remember that dispersion forces, though they are on average the weakest type of attractive force, can be very strong, and their strength increases as carbon chain length increases. And as a hydrocarbon or any molecule or any atom in general is larger, has a larger electron cloud, more electrons, more polarizable. These are all things that we've talked about before. Functional groups that make a chain polar include anything with our carbonyl carbons. So we have aldehydes and ketones and carboxylic acids, halogens as well, as we saw with substitution reactions. That bond between carbon and a halogen is very polar, making the molecule as a whole sometimes pretty polar. Be mindful of the functional groups in a molecule that will allow for hydrogen bonding. These, of course, are a hydroxyl group on an alcohol, the NH2 or amino group on an amine, carboxylic acid functional group, COOH, and then functional group in an amide, C double bond O and H2. So each of these, the presence of each of these allows for molecules to hydrogen bond, giving these substances stronger attractive forces, higher boiling points, higher melting points, things of that nature. Lots of different examples. Here's a common one. So there are two isomers that have this chemical formula, and they have very different boiling points. So come up with two different structures for this substance, and then we'll talk about the difference in their physical properties. Go ahead and pause now. All right, so these are known as functional group isomers. They have a different functional group. We have ethanol and dimethyl ether. And so we see that this is, even though this has an oxygen here, this molecule is fairly non-polar, even though we have some polar bonds in there. It's a rather symmetrical molecule. In ethanol, we have a hydroxyl group, which lends itself to hydrogen bonding. So even though these two substances have the same chemical formula, their structures result in very different properties. So ethanol, having hydrogen bonding, will have a much higher boiling point than dimethyl ether. So ethanol has a boiling point of around 78 degrees Celsius, dimethyl ether boiling point of about a negative 11 degrees Celsius. If you look in your textbook on the bottom of page 481, it shows a flow chart, if you will, a list of substances, and has volatility there. So remember, there's a relationship between volatility and attractive forces, and attractive force and boiling points, actually all on there. So we have the most volatile of these substances listed there are alkanes. So alkanes being the most nonpolar of the compounds that we've discussed so far. They will have just dispersion forces, leading to rather low boiling points. Followed by halogenoalkanes. So again, that's presence of a halogen makes for a somewhat polar molecule. So we have dipole-dipole forces. And then aldehydes, that's carbonyl carbon. That bond between carbon and oxygen is rather polar, making aldehydes rather polar molecules, also exhibiting dipole-dipole forces. Same thing with ketones, we have same functional group there. And so same situation with aldehydes. Alcohols, as we saw in this example, hydroxyl group giving way to hydrogen bonding. And then lastly, carboxylic acids having the lowest volatility, having the highest boiling points. We have both that very polar CO bond, and then we have a hydroxyl group as well. So be familiar with the properties of a substance that affect the physical properties such as boiling point. All right, next up we have polymerization, formation of polymers or large molecules. So polymers are very large molecules made by bonding together smaller molecules called monomers. We have two types of polymers. We have addition polymers, and then we have condensation polymers. So just like what we talked about with addition reactions, an addition polymer involves just combining monomers without the formation of another product, so there are no byproducts. These often contain double bonds that are broken to make the polymer. So there's lots of examples. Some of them include ethene. So ethene molecules can combine or form rather long chains called polyethene. Propene is another monomer that can be used to build polypropene is the polymer. Chloroethene. So just like ethene, but with a chlorofunctional group. These are also known as vinyl chloride. And so these can combine to form a polymer called polychloroethene or polyvinyl chloride, otherwise known as PVC. And then the last one is styrene, which of course can form the polymer polystyrene, which we have used in our calorimeters. So for examples of structural formulas for both the monomers and polymers, you can take a look in your textbooks. Actually, in the option section, option A, material science, this one's on page 618 to see examples of those and to see how these substances form. All right, with condensation polymers, just like our regular condensation reactions we talked about in previous lessons, you have two substances that combine to make a larger substance with the formation of a smaller molecule as a byproduct. The most common byproduct is water because the reaction is often an esterification or amide formation, and we saw examples of that. There are other substances that can be produced as a byproduct as well, such as HCl or NH3. So it just depends on the particular type of polymerization reaction. All right, so these are also found in option A, material science in your textbook, pages 653 to 656. We'll start with polyamides, and there's a couple examples you need to know. One of them is called, whoops, let's try that again, 6,6 nylon, or just nylon in general. What's important to know here is the reaction that produces nylon. And so your reactants are 1,6-diaminohexane and hexane dioic acid. Dioic. Let's see if I can spell that correctly. So 1,6-diaminohexane and hexane dioic acid. So notice both of these molecules we have in the one we have amino group on opposite ends, allowing for the formation of chains, and likewise on hexane dioic acid we have our hydroxyl group or carboxylic acid group on opposite ends, and we can just have many of these linked together. So in this case we have the hydrogen from an amino group and our hydroxyl group from the acid. Bond forms between nitrogen of the amino group and carbon of our acid group to form the bond between the two monomers, and we get, of course, water as the other product. Another example of a condensation polymer similar to nylon is Kevlar. So let me clear this out so we can write that. Kevlar, which is used in bulletproof vests, involves the combination or combining of similar to nylon, except instead of having hexane chains, we have benzene rings. And so we have so again, we got two carboxylic acid functional groups on opposite ends of our benzene ring. So benzene 1,4-dioic acid, and the P stands for para, and para equals 1,4. So if you have the same functional group at 1 and 4, that is called para. We have 1,4, oops, sorry, not 1,4, para diaminobenzene. So again, same as a reaction that forms nylon, but instead of hexane chains, we have benzene rings. Same idea, the hydrogen of the amino group will combine with the hydroxyl group of the acid to make your water, and then we have a bond forming between nitrogen and carbon to give rise to our polyamide. Instead of polyamides, we have polyesters. Esterification reactions involve a reaction between carboxylic acid and an alcohol. So the example you need to know is PET. PET is a polyester. We have ethane 1,2-diol, so that's our alcohol, reacts with our acid benzene, again 1,4-dioic acid. So this will result in the formation of PET. We can see an example of this on page 654. And we have one more polymerization reaction, involves the formation of peptide bonds. These are, again, polyamides. We saw an example of this the other day. So page 684 to 685, this is in the biochemistry section of your textbook. So let's draw a couple amino acids. So we're talking about the bond between amino acids to form a dipeptide or polypeptide. So let me draw that out. So all the amino acids have an amino group and an acid group. And then what makes them different is this R group. So I labeled it R1 and R2. So again, we have our water, the results of, whoops, I did that wrong. Let's back up. There we go. Let's try that again. One of these hydrogens, so maybe I should draw that out again, just so you can see. Hydroxyl group from the acid, hydrogen from the amino group. We have a bond that forms between this nitrogen and this carbon, and that is our formation of our amide. And so if you link a bunch of these together, you get a polyamide. Bonds between amino acids we call peptide bonds, and a bunch of amino acids together, bonded together, makes a polypeptide. That concludes this lesson. I'm going to make another video on synthetic routes and knowing how to form a particular substance given some reactants. All right, thanks for watching.